Welcome to our channel. Today, we will take you on an extraordinary journey to one of the most extreme limits of our universe, absolute cold. Have you ever wondered if there is a limit to temperature, a point beyond which you can't go? Today, we will explore an invisible and unreachable boundary that has fascinated physicists and scientists for centuries. Absolute zero, a temperature so low that, theoretically, it cannot be surpassed. Imagine an incredibly cold universe. We're not talking about the freezing nights of Antarctica or the extreme temperatures of the icy deserts on our planet. We're talking about places so cold that even the concept of cold becomes almost abstract. Yet, such places do indeed exist, scattered across the universe. If we wanted to find concrete examples of extreme cold in our solar system, we could look at Pluto, the distant and mysterious dwarf planet orbiting the outskirts of our solar system. Pluto is one of the coldest objects we know, with an average surface temperature of around 228 degrees Celsius, 378 degrees Fahrenheit. To give you an idea, on Pluto it's so cold that most of the gases we breathe on Earth, like oxygen and nitrogen, would freeze into solid form. But Pluto is not alone. Cosmic cold can also be found on fascinating moons like Europa, one of Jupiter's main satellites. Europa is particularly interesting to science because, beneath its icy crust, it could hide a liquid ocean. However, the temperature on its surface drops to 223 degrees Celsius, 369 degrees Fahrenheit, creating a hostile, icy environment. Despite these impressive numbers, the coldest temperatures we can measure in the cosmos are nothing compared to the theoretical temperature that is absolute zero. Absolute zero is a temperature that marks the lowest possible limit on any thermodynamic scale. This extreme point is defined as 273.15 degrees Celsius, 0 Kelvin, and it is the point at which the motion of the particles that make up matter almost completely stops. But what does it really mean to stop the motion of particles? To understand this concept, we must first examine what temperature is. Temperature is nothing more than a measure of the average kinetic energy of the atoms and molecules within a substance. Imagine molecules as tiny marbles that continuously move and vibrate. The higher the temperature, the faster these particles move. When we heat a substance, we add energy in the form of heat, which accelerates the movement of its particles. When we cool a substance, we reduce this energy, and the particles slow down. At normal temperatures, like those we experience daily, the particles move at speeds we cannot perceive. But when we reach very low temperatures, such as those near absolute zero, the movement of the particles slows drastically to the point of almost stopping. But here's the paradox. According to quantum mechanics, particles can never completely stop, not even at absolute zero. This is a surprising and difficult concept to imagine, but it is one of the fundamental laws of the universe. Even when a substance is cooled to absolute zero, the particles still retain a small amount of energy called zero-point energy. This phenomenon is closely related to Heisenberg's uncertainty principle, one of the most famous principles in quantum physics. It states that it is impossible to know both the position and velocity of a particle simultaneously and precisely. This principle imposes a limit on how accurately we can measure the microscopic world and, at the same time, tells us that particles can never be completely motionless. Even at absolute zero, particles possess a minimum of residual energy. Reaching absolute zero is an unattainable dream. No matter how hard we try, we can never bring a substance to 0 Kelvin. Why? The reason lies in the fundamental limits of physics. When we cool a substance, the energy we can remove becomes smaller and smaller as we approach this extreme temperature. It's like trying to walk while taking ever smaller steps. You can get closer, but you will never reach the goal. Over time, scientists have developed sophisticated techniques to achieve extremely low temperatures. One of these techniques is laser cooling, in which lasers are used to slow the movement of particles, thus reducing their thermal energy. Another technique is evaporative cooling, where the most energetic atoms in a gas are removed, lowering the overall temperature of the system. Despite all the technological advancements, getting close to absolute zero comes with increasing difficulties. When temperatures approach just a few billionths of a degree above absolute zero, the results become more limited, and improvements are increasingly hard to achieve. In a groundbreaking experiment, researchers managed to reach a temperature below absolute zero. How is that possible? This surprising result was achieved by manipulating quantum systems in such a way as to create a negative temperature, but only for a fraction of a second and under very specific conditions. While fascinating, this result has no immediate practical implications but represents a scientific curiosity that highlights the complexity of our universe. Now that we understand how difficult it is to reach absolute zero, you may wonder, why do scientists push to reach such low temperatures? The answer lies in the fact that, at these extreme temperatures, matter behaves in entirely new and unexpected ways. When particles approach absolute zero, quantum effects begin to manifest that would be completely hidden at normal temperatures. For example, it's at these temperatures that phenomena like superconductivity occur, where materials can conduct electricity without resistance, or superfluidity, where liquids can flow without friction. These extreme conditions also allow the study of materials and particles in ways that help us better understand the fundamental laws of the universe. The applications of these discoveries could lead to innovations in fields such as quantum computing and superconductivity, two areas that could revolutionize modern technology. In conclusion, absolute zero represents an insurmountable theoretical limit. Despite our efforts to approach it, particles always retain a minimum of residual energy that prevents us from reaching this extreme condition. It is a boundary imposed by nature itself, but one that continues to fuel our scientific curiosity. Thank you for joining us on this fascinating exploration of the extremes of temperature. If you found this journey into the mystery of absolute zero interesting, don't forget to hit like, share the video, and subscribe to the channel to discover more fascinating secrets of the universe.